Okay, so the question is to find the multiplicative inverse of 15 in Z37. So Z37 is is the set of all possible remainders when any integer is divided by 37. And we're just keeping it in the positive, and those remainders would be 0, 1, 2, and so on, right up to 36. So that's a set of all possible remainders if you divide any integer by 37. Right, and so now what we're looking for is the multiplicative inverse. Now, in normal arithmetic, if I was to actually find the inverse of 5, for example, it'd be 5 multiplied by the multiplicative inverse would equal 1. So the number that goes in here would be 1/5, because 5 times 1/5 equals 1. Every positive integer has a multiplicative inverse, right? So that means the multiplicative inverse, MI for short, of 5 is 1/5. This is in normal arithmetic. Now, if you want to look at it in modular arithmetic, what we have is 15 has to be multiplied by its multiplicative inverse, mod 37, and we'll give a remainder of 1. So we're saying if 15 is multiplied by a number, and that number is then divided by 37, 37 will go into it so many times with a remainder of 1. So what you do now is you look at 37 and say 37, 137 is 37. 2 37s are, let's see, 2 37s are 74. And you could go on, 3 37s are 111. But we're looking for something that 15 will go into if you add one more to it. So you could say, well, consider 75, right? Because it's one more than this. And 15 goes into 75 evenly. So 15 goes into 75 5 times, right? 5 15s are 75. And 37 goes into 75 twice, which will make 2 37s are 74, with a remainder of 1. So it has a remainder of 1. And that's the one that goes up here, right? So we can now say that 15 multiplied by 5 mod 37 equals 1, i.e. 75 mod 37 is 1. So that means that the multiplicative inverse for 15 in Z37 is 5. And that's your answer. Okay, now, I did it again. I just have to make this canvas size bigger. Okay, right. So now there's another one. Now this is, if I'm interpreting this notation properly, you're given that Z21, 5x equals 3. And you have to solve. So my interpretation of this is, if you have 5 and you multiply it by some number, mod 21, the remainder is 3. So 5 multiplied by some number, then that divided by 21 will give you a remainder of 3. So if we consider the things at 20, like 121 is 21. 2 21s are 42. Now, we're looking at mod 3. So 42 plus 3 is equal to 45. It ends in 5, so it's the number that 5 goes into. Okay, so now you can say, well, 5 times 15 is equal to 45. And if you consider it, 45 mod 21 will be 3. Because if you divide 21 into 45, it goes twice. 2 21s are 42 with a remainder of 3. So that means that 5 times 15 mod 21 equals 3. So the solution is x equals 15. Okay, now I'm going to do some exam papers, some questions that have cropped up in exam papers, really to just reinforce the idea of the multiplicative inverse. So for example, in 2018 was year 3, and this is question 2b. It says calculate the greatest common divisor. So I just write for short, find the greatest common divisor of 7 and 19. And find the MI of 7, the multiplicative inverse. The multiplicative inverse of 7 in Z19, if it exists. A lot of numbers don't have a multiplicative inverse. Okay, so the greatest common divisor of 7 and 19, that is the largest number that will divide both into 7 and into 19. In this case, 7 is prime. So the only two divisors it has are 1 and 7. 19 is also prime. So its divisors are just 1 and 19. That means the only common divisor they both have is 1. So the greatest common divisor of 7 and 19 is equal to 1. Now when this happens, when you have two numbers, they don't necessarily have to be prime, but if their greatest common divisor is 1, that means they're prime to each other. So those two numbers are considered to be relatively prime. Now I'll just go off a little tangent here. Sorry. But the greatest common denominator, or the greatest common divisor of, say, 8 and 9 is also 1. Now 8 is not prime. It has 1, 2, 4, and 8 as divisors. And 9 is not prime either, and it has 1, 3, and 9 as divisors. But they have a greatest common divisor of 1. So 8 and 9 are relatively prime to each other, right? So 8 and 9 are relatively prime. Sometimes that's called coprime. So that's just on the side, right? So now we know, get back to the question, the greatest common divisor of 7 and 19 is 1. When numbers are relatively prime, then there does exist a multiplicative inverse. So there is a multiplicative inverse for 7 and 19 in Z19. Because they are relatively prime, i.e. their greatest common divisor is 1. So then to do this, then you would look at all the multiples of 19 first of all. So you have 1 19 is 19, 2 19s are 38, 3 19s are 57, and 4 19s are 76. And you have to look now, if we add, remember, for a number to be relatively prime, we have to say that 7 multiplied by its multiplicative inverse, mod 19, equals 1, i.e. there will be a remainder of 1 when 7 multiplied by a certain number after it's divided by 19 will give a remainder of 1. So the thing is, if we add 1 to any of these, 27 doesn't go into that, 39, 7 doesn't go into that, so we're adding 1 to them. 58, 57 plus 1 is 58, 7 doesn't go into that. But this one, 76 plus 1 is 77, and 7 goes into that because 7 times 11 is 77, right? And then you check 19. Well, we know 19 goes into 77, 1, 2, 3, 4 times with a remainder of 1. So this remainder here is the indicator that it's going to be relatively prime, or that we have a multiplicative inverse. So now we can say that 7 multiplied by 11 mod 19 equals 1. Because that's the same as 77 mod 19, which is 1. Therefore, 11 is the multiplicative inverse of 7 in Z19. I'll leave that at that.